Hi everyone, this is Kenny Lee, and today we're going to talk a little bit about electric fields and forces. So starting off with the electric field kind of acts like a feeler for the charges. Its symbol is a capital E, and it is sometimes what we call a force field, where these lines come out and act like sensors for that electron. The way we find the electric field is by Q is the charge, over R squared, the distance out from the charge that we want to measure. Now, electric field's measured in newtons per coulomb. Now, if you haven't already done so, go look at the video about Coulomb's law, because that goes along with this as well. Another way that we see the equation for electric field is written like this: 1 over 4 pi epsilon naught Q over R squared. Epsilon naught is the vacuum permeability of space for electric fields, and it's this number, 8.85 times 10 to the negative 12, but you usually don't see it in that form much anymore. Usually you see it more in this form, just using the value of K, which is the same thing as that, is just 9 times 10 to the ninth, and then our unit to make sure everything comes out to be in newtons. Charge is measured in coulombs, and distance is, of course, measured in meters, and that's the distance out from the charge. So if the charge is here, and we want to look at some point out here, that is the distance R. So the field coming out of that, how strong it is by the time it gets to this point at some distance away from the charge. Okay, so let's go ahead and get into two things with this video. We're going to work on the electric field drawings, and we're going to do the calculations as well. So let's get into the drawings first. Okay, for drawing the electric field, there's basically two rules. One, the electric fields always come out of positive charges, and they always go into negative charges. And two, the electric field lines can never cross, so that you won't see two electric field lines go through each other like this. If they come towards each other, they'll actually bend each other and deflect. And so they will never cross. You never should do this on your drawings. So for this one, I've got a positive charge, so this is going to be a proton, or maybe just some object that's charged positively. Well, the electric field lines come out radially from that charge as best you can. And the more lines, the stronger the field. Okay. They should always end in arrowheads. For this one, that's a negative charge, so that's an electron or something that's got an excess of electrons, so it's negatively charged. The electric field lines go into the negative charges. So they come out of positive charges and go into negative charges. Okay. So what happens if we get these two charges close to each other? Well, field lines come out of positive charges, go into negative charges, so they will actually connect these two. And this is how the charges know what's around them, is by how these fields interact with each other. And so you should get something that looks like this. Now, not all the lines will actually go there. Some of these will just go out into space and go into another negative charge someplace else. And these will get field lines from some other positive charges out there someplace in space. They should come in like radially. That one's curved a little bit. But they all, again, should have arrowheads on them someplace. Now, what if we've got two positive charges? Again, the field lines come out of positive charges. Okay, that's no problem there. But what about the field in between? Well, if we've got a line coming out this way and a line coming out this way, as they come close to each other, they're going to bend and deflect. So this will curve up, and that will curve up. And so you'll see, if we draw it nicer, something that looks like this. And even lines like this, again, can never cross. They will come really close, and the tighter they are, the more force is there, but they should never cross. And those field lines kind of act like a spring. There's a law called law of charge. And the law of charge basically says opposites attract and likes repel. So here we have opposites. the field lines mesh together, kind of interweave, and actually would pull those two charges together. On this one, those field lines are pressing against each other, sort of like a spring. They want to bounce back off and throw these two charges away from each other. So these two charges will want to repel each other. So those are attract that repels. All right, let's see what the math looks like. Okay, so our equation is the electric field is equal to K, that constant, which is 9 times 10 to the 9th newtons meters squared over coulomb squared. Make that 9 better. And we want to figure out the electric field from this charge at some distance in space, apparently half a meter away from it. So it's really kind of a plug and chug. The electric field, which is a vector, by the way. We drew arrowheads, so electric field's a vector. It's equal to K, the value of the charge, divided by the distance between the charge and the point you're looking at squared. Now, a lot of times you'll see people use absolute values for this. And I can understand why. It's because we're just looking for the value of the strength. They don't really care about the direction, but I think the direction is important. So I am not going to put absolute values on here. We're going to go ahead and keep the sign as is. So we get 9 times 10 to the 9th times the charge, which is 7 coulombs, divided by how far out we're going to look. So we're looking at half a meter away from the charge. So we'll give this a calculation. So 9 times 10 to the 9th times 7 divided by 0.5 squared gives us a value of 2.52 times 10 to the 11th newtons per coulomb. That would be the value of the electric field. Now, the reason why I like not using absolute values is because this comes out to be positive. So I know the electric field is going away from this charge. No matter where it is, if it's left, the field's going left. The spots to the right of the charge is going right. If it's above it, the field's going up. This tells me that the field is going away from the charge. So that's why I like it instead of using just absolute values. Let's try a couple more where we solve for some of the other stuff here. Okay, so here's one where I give you an example of that. So we got a -5 coulomb charge. So that has an object that has more electrons than protons, enough to get a charge of 5 coulombs. We want to see about the electric field around it. If the field has this value at some location, I want to figure out where that location is. How far away from the charge is it? So again, E equals K Q over R squared. The electric field was -2.8 times 10 to the 9th. K is 9 times 10 to the 9th. Q is -5, or -5, I should say. And R, we don't know. Okay, now there's a trick that I like to do when I'm solving for this bottom. I call it the super secret math trick. And basically, we swap these two. R squared comes out, and that takes its place. So 9 times 10 to the 9th times -5 divided by -2.8 times 10 to the 9th. So we do that calculation and take the square root. So 9 times 10 to the 9th times 5 negative. I really don't have to do the negative because we know those are kind of cancel out, but I'll put it in the calculator anyway. Divided by 2.8 negative times 10 to the 9th. And we get that, but we're not done. That is 16.07. But I need to take the square root because I don't want R squared, I want R. So I'll take the square root of that. And so this spot is about 4 meters from that charge. Let's do one where we actually find the value of the charge. A charged object produces an electric field that has that value, strong, misspelled strong, at a distance of 6 meters from the object. What is the charge of the object? So again, E equals KQ over R. Electric field is 12,500. By the way, numbers can be very large. The electric force and thus the electric field, K is 9 times 10 to the 9th. So that's a very large number. So you're going to get much, much larger numbers than back when we did something like this for gravity. So back to this. So K is 9 times 10 to the 9th. Don't forget that. Q, we don't know Q. But we do know it's 6 meters from the charge that we found this value of the electric field, and that's got to be squared. So now we just go ahead and work this. So 12500, and we go ahead and times 6 squared, because that comes up, so it'll be 12500 times 6 squared, and then we're going to divide by 9 times 10 to the 9th to get Q. So we move that down and that up. Divide by 9 times 10 to the 9th. And we get a value of our charge to be 5 times 10 to the minus 5 coulombs, which is perfectly okay. The charge of just one electron is 1.6 times 10 to the negative 19 coulombs. So there's still a lot of charges there. Okay, let's take a different look at these electric fields. Let's say we've got a region of space where there's already an electric field, and we don't worry about where it came from. It's just some charge distribution produced it. So if we don't know, what we can do is we can still figure out, well, even if we don't know the distribution of charge that creates that field, we can still figure out the force if we put a charge in that field by using this. So the electric force is equal to the electric field times the charge you place in there. Now, Coulomb's law is Q1, Q2 over R squared. And so the electric field is just this first part here. So we can also find it by doing that. And that's the equation I'm going to use here. Because we got a region of space that already has an electric field of 8 newtons per coulomb. And we're going to drop an electron in that field to see what happens. Okay? So, here we go. Electric force is equal to EQ. And so the electric field was 8. Charge on electron is negative 1.6 times 10 to the minus 19 coulombs. And so if we do this, we get 8 times 1.6, make that negative, times 10 to the negative 19. And so we get a value of the electric force to be negative 1.28 times 10 to the minus 18 newtons. That's the force that electron in that field would feel when it's placed in that electric field. And then we can go back and do some interesting stuff. We can do F equals ma with the mass of the electron and actually figure out the acceleration of that electron when we place it in the field. Now, what if it was a positive charge, like a proton, instead of a negative charge? So if it was positive charge placed in there, we still get Fe equals EQ. So we're still going to get the electric field is still 8. The charge for a proton is positive 1.6 times 10 to the minus 19 coulombs. So we would get a positive 1.28 times 10 to the minus 18 newtons. So both charges would feel the same force, but since a proton is much more massive than the electron, the proton will have a smaller acceleration than the electron does. If we look at this, let's think about this electric field. So remember, electric field lines come out of positive charges, go into negative charges. So even though that we don't know the distribution, we know that over on the left-hand side, there has to be positive charges over here someplace, and negative charges over here someplace, because electric field lines always come out positive charges, always go into negative charges. So when we place this electron in there, we know it feels this force, but which way would it go? Well, a couple of things. Remember, opposites attract and likes repel. So if positive charges had to be over here and negative charges had to be over here to create that electric field, this electron will want to go towards opposite, so it will want to go in that direction. The proton will do the exact opposite. It will want to go in this direction from that force. So that positive and negative sign does give us some beneficial information. Okay, so can we have charges and still have no electric field? Yeah, and it happens quite a bit. So we want to set up some things where the electric field is zero. And we can do it a couple different ways. We're going to start off drawing a diagram, and then we'll actually do the math. So let's say we've got two 5 coulomb charges 4 meters apart. If I was just to draw the electric field lines, they would look something like this, and they would all deflect around this one spot in the middle. So right there in the very center, since these are two identical charges, that's where the electric field would be zero. So we can get that graphically because all the lines will bend away from that whenever we draw them in. But what happens if we actually try to do it mathematically? So we want to have the electric field equal zero. Now the electric field's a vector. So if we say going to the right is positive, anything going to the left is negative. So the electric field lines from this one are positive, electric field lines from this one is negative. So if we say the electric field from this first one plus the electric field from the second one has to equal zero. And we know since this electric field is going to the left, it's negative. Move that over, so the electric field from one has to equal the electric field from the other one. And now we can just put the numbers in. So since both charges were the same, KQ over R squared equals KQ over R squared. K's were the same, the charges were the same, so that means R's have got to be the same. So whatever this R is also what that one is. Only way that works is if these are both 2. Because we only have 4 meters in between this. So if the distance from this one has to equal the distance from this one, that means it has to be in the middle. So that means 2 meters from either charge, that's where the electric field is zero, right in between the two charges. And kind of along that line is, well, just really dead center. Now, what if they're not the same charge? That's where it gets a little bit more creative. Because again, this charge is more powerful from that than this one. So this one's going to push that spot closer to the weaker charge. It's still going to be there, but now it won't be in the center because this one's more powerful than that one. So we have to play a little bit of a math game. If this is 4 meters, then let's say the distance out to this spot is R. And so the distance from here to here has got to be 4 minus R. So if this is like 3, then 4 minus 3 is 1, so this had to be 1 meter. 3 plus 1 is 4, so that will be it. That's probably not the answer, but that was a good illustration. Now to do this one, again, the electric field from this one has to equal the electric field from the other one, because they've got to cancel each other out, just like the summation that we did here. So I want to go ahead and write it out in that form. So K Q1 over R squared, because we're going to use that R, equals K, the second charge, Q2, and this one will be 4 minus R, because we don't know what R is. Now, we do have one thing that can simplify this. There's a K on both sides, so they can cancel out. That Q is 5 over some R we don't know. This charge is 3 over this 4 minus R squared. Now, I don't know about you, but I hate the quadratic formula. So I want to do a trick. I want to take the square root of both sides. And when I do, this is what happens. Square root of 5, well, that's a number. I can type it into my calculator and figure that out. Square root of R squared is just R. The square root and the squares cancel each other out. Same thing over here. This is going to be square root of 3, but that square root in this squared is going to just be 4 minus R. And now what I can do is cross multiply. So I want to cross multiply these two. So I'm going to move it over here so I have a little bit more space. So square root of 5 times 4 minus R equals square root of 3 times R. I just cross multiplied. And now let's distribute this. So 4 square roots of 5 minus square root of 5R equals square root of 3R. I'm going to move this over. So 4 square roots of 5 equals, when I move that over, it becomes positive. So we get square root of 3R plus square root of 5R. And I want to combine these two. We get 4 square roots of 5 equals square root of 3 plus the square root of 5R. And what I'm going to do is I'm going to go ahead and use the magic of calculators to figure out these numbers. So square root of 5 is that times 4 is 8.94. Square root of 3, whoops, wrong button. Square root of 3 plus the square root of 5 equals 3.97R. And then I want to divide by that 3.97. So 8.94 divided by 3.97 gives me a value of R of 2.25 meters. So here's the long and short of it. That point is going to be 2.25 meters from this charge, and then 4 minus 2.25. So this distance is going to be 1.75 meters from that charge. That's where that spot's located. And that's the most intense math here for this one. It's just doing those two charges and finding out where that point is where the electric field is 0. It's always going to be pushed towards the weaker charge. All right, one more thing. Where else is the electric field 0? Well, inside any conductor or conducting loop. So if I've got a conducting loop, that's just like a wire ring, and I've got an electric field coming through here. That's my electric field. The electric field inside this loop, or inside this disc, or inside this block, is all going to be 0. There's not going to be an electric field inside there. What happens is, well, sometimes the electric field just passes, but if the electric field hits, it just reemerges on the other side. Sometimes they look a little bit nicer where they come in and then go back out like that. But the electric field is going to just kind of be absorbed and re-emitted by this. Same thing for the disc. Electric field can probably dip towards it and then come back out and keep going if it misses, but really it's going to be absorbed and re-emitted on the other side. So the electric field on the inside of this will not have one. So it's always 0 inside there. So the electric field would just pass through. And inside any of these solids, like a solid or even a loop of metal, it actually acts as shielding, and so the electric field on the inside is 0. And the electric field just kind of passes around. All right, well, thank you for watching the video. Tune in some more for some more videos about physics. Thank you, and goodbye.